Hello everyone. So today I want to talk to you about Boolean algebra. And Boolean algebra is a technique to simplify our circuits, or to more accurately simplify the logic expressions. Now might want to ask, like, why do we need to do this? Well, here's a very nice circuit right here that has 1, 2, 3, 4, 5, 6, 7 logic gates. Now, if you guys remember breadboarding your tripwire, this is tripwire times 7. That's how much effort this requires. So this is a lot of effort. It's not, impossible, and it does get better the more you practice breadboards and logic gates. But still, it's a highly unpleasant circuit. Well, it turns out if we use Boolean algebra and simplify this, we will end up with this circuit. It has only 2 logic gates. So that sounds pretty awesome because that means we have to do way less work. All right. So basically anything that let us go from 7 logic gates to 2 is a good thing in my opinion. Okay, so let's figure out let's learn why this is a Boolean algebra. Why this is called a Boolean algebra. Oh. Well, it all comes down to this guy. Well, his name is George Boole, and he was kind of Captain Obvious of 19th century. And you will see very soon why I'm saying this. So he was a mathematician, and he worked a lot with binary numbers and logic expressions. And in 19th century, no one really got like why he was bothering to do what he was doing. But somewhere in the middle of 20th century, people started to build computers, and his research became very, very, very valuable. Okay, so let's take a look at his theorems. And this is why I'm saying the guy's basically Captain Obvious, because the theorems are very, very obvious. So our first theorem is that x times 0 is 0. But remember, this is not a 0. This is x and 0. So over here, you have an AND gate, and you have an input x coming in, and you have an input 0 coming in. Well, here's the deal. For your AND gate, you only get 1. It's the bottom column right here. If both of them are 1. So if one of them is always 0, the output will always be 0. So over here in this little table, you can see that I crossed out the outputs that are completely impossible. Because in this y value over here, I always have 0. So I never have 1 there. So the only outputs I have are zeros. That sounds pretty straightforward. So let's take a look at the next one. And the next one says x and 1 is always x. So the same logic applies, guys. So over here, I'm crossing out in this truth table the values that are impossible. So now my y value can never be 0. It's only a 1. So if x is a 0, and this is a 1, then I get a 0 because it's an AND gate. And if x is a 1, and this is always a 1, I get a 1. So when you look at your outputs, they match up exactly to the inputs if it's x. So these ones kind of look a little bit like math. You've seen this in your regular math class. X times 0 is 0, x times 1 is x. This one, however, does not. Because x times x is not x squared. There is no such thing as x squared in logic. So what happens if we put in 2 x's inside? Well, this one will have a 0, and this one will have a 0. So I'll have a 0 in the output. Well, what if I have a 1? Then I have 1 also at once. And that means I will have 1 in the output. These 2 values that I'm crossing out over here, they are impossible, right? Because if this one is a 0, this one also have to be 0. They're the same. So x and x is just x. So it's kind of like I like cats and I like cats. Basically, I just like cats, right? I don't like cats squared. You don't square a cat. Okay, so next one. X and not x equals 0. In other words, x and not x is false, always. This one is kind of like saying I like cats and I don't like cats. You can't be both at the same time, okay? You can't be like, I'm passing Miss M's class and I'm not passing Miss M's class at the same time. Nope. You're either passing or you're not. But it's not both of them at the same time. So that output is always false. And if you will look, I have crossed out over here the lines that are also impossible in this case. And those are the lines where x and y are the same. So the remaining ones, you can see they always give you 0. So these theorems are pretty straightforward, actually. There is really nothing difficult about them. So these are the ones that Boole extracted from the AND, right? From the AND function or AND gate. So there, it makes sense that it would have to be the one with the OR gate. All right, guys, so here's the one with the OR gate. And it follows exactly the same logic. We put the different kind of inputs into our OR gate, and then we just look through them. So this one has x or 0 going into the OR gate. Well, remember how the OR gate works. You can only get a 0 if both of your inputs are 0. So if x is 0, you will get a 0. But if x is 1, you will get a 1. So the output matches x exactly. So the output really is just x itself. So once again, I'm crossing out over here the values that I do not have, because my y value is always 0. I cannot have this or this. Okay, so next one is x plus 1 equals 1. Okay, this one is the most obvious one of them all. If, remember how OR gate works, right? Only 0 and 0, 0 or 0, 2 zeros going into the OR gate will give you a 0. If one of them is always 1, you will always guess the 1 out. So next one, x or x equals x. Well, this is like saying, bring me a hamburger or bring me a hamburger. Well, it kind of makes sense that you just bring me a hamburger, right? So that's it. So if you study this this truth table, you'll see that once again, these are impossible values. And the next one is x or not x equals 1. Well, this is like saying I'm passing Miss M's class or I'm not passing Miss M's class. Well, that's true. That describes every single person, right? So whether you are passing my class or you're not passing my class, it's true. All right. So next one would be the rules that we would get out of the inverter. And we only have one rule over there. And the rule is very, very simple. Basically, if you invert your signal twice, you will get exactly the same signal out. So this is how it works. You put an x through the inverter, it becomes a not x. You put a not x through the inverter, it becomes a not x. But when you look at the truth table, the not x is just x itself. So that's pretty straightforward. So next is I want to show you an example how to use those theorems. So far we have 9. Just the AND ones, the OR ones, and one inverter. All right, so here I have an expression, FAAB plus C not CD. All right, so first let's take a look over here. I have A and A itself. So if you remember, one of our rules was x times x is just x, right? It's not x squared. So I can substitute A for those two A's because it's the same thing. Now let's look at this rule. I have a C and not C at the same time. That was rule number 4, and this is the statement that's always false, right? You pass my class and you don't pass my class at the same time. That doesn't happen. So that one always comes out to be 0. And of course, another rule that we got is that 0 times x is always 0. So this comes out to AB plus 0. And as we have already discovered, AB plus 0 is just AB. It's what the rule is what the rule is. Now, I want to draw your attention to the fact that we just went from a number of logic gates. Let's see, we have 1, 2, 3, 4, 5, 6 logic gates to 1. That's a pretty good simplification because this literally 30 seconds of work just gave us time savings of several hours of wiring those logic gates. Here's another example. I have B, B, not C, B, not C, not C, or A, not A, B, 1, or A, not B, 0. Okay. Well, once again, I'm going to go ahead and underline the ones where I have some kind of rules. So over here, I have two of the same terms going into n, okay? So that's just B. Over here, I have two of the same terms going into n today. So that's just not C. Okay, I need to calibrate my smartboard. All right, so you can see I have B and B itself. So that's just B. Not C and not C itself. That's just not C. Then the next term I have not A, B, and 1. Well, if you remember, guys, we have a rule that said that x times 1 is just x. So I'm going to use this rule, and I think that this term is just not A, B. And the last one, I have A not B times 0. So x times 0 is only 0. So that whole term is going to become 0. Okay, so let's flip it. So now I have B not C, B not C, and then I have not A, B. Alright. So once again, I have two terms that are very, very similar. I have B not C twice. And if you remember your OR gate theorems, any input twice is just itself. So A plus X plus X is just X. So this is exactly what I'm going to do. So my final answer is B not C plus not A, B. Well, that's a lot better than this whole big thing that we had up front. Because I don't even want to count how many logic gates there are over here, but I can clearly see that there are 1, 2, 3, 4, 5 logic gates in this expression on the bottom. These are not all the laws that we have. We also have commutative law. And commutative law is very, very, very useful. It seems to you like it's the most obvious thing in the world, but here's the thing. There are plenty of mathematical constructs that do not actually use the commutative law, like matrices in your Algebra 2 class. If we couldn't change places of our inputs, like we do, like it's shown over here on the screen, then it would be very, very difficult to simplify things. So this is a very useful and very nice law to have. So the next one is we have associative law. And that one basically says that you can group your inputs any way you like. So you can put the parentheses any way it's convenient to you. And that is very good. We actually use that a lot. Basically, the main strategy for simplifying expression is to group terms together inside the parentheses and then factorize something, see if something inside the parentheses cancels out, and then redistribute it back. So that kind of brings me to the next law we have, and that is, of course, the distributive law. So I know that you guys learned all about FOIL method or whatever the heck you guys call it. Well, I'm not a big fan of any kind of silly acronyms. I just say draw the arrows and use them. So over here I have this arrow coming from X to Y. So I get XY. Plus, I get the other arrow, and that's X, Z. Over here I have same kind of deal. Only I have arrows on the top and on the bottom. Very, very straightforward. Okay? So even if you don't know how to distribute, and you really should have learned that in like 7th grade or something, or 6th grade, or, well, I actually learned this in 4th grade. I don't know, like, I don't know when you guys learn this, okay? So just use what you learned. And if you haven't, this is how you do it. So let's do another example. Let's go ahead and solve this one out. So you can see I have some really nice terms over here in parentheses. And just when I look at it like this, it doesn't seem to give me any kind of simplification when I'm looking at it. So if you look at your expression and you have parentheses like this, and you see no simplifications, distribute. So that's what I'm going to do. Oh, right. So I've distributed them all, and you can immediately see that I have one term that kills itself. I have R, not R. That's like having X and not X. So this is always 0. So my new expression is not R. Okay, so now that we have 4 terms instead of 5, it's a little better, but it's still not all that great because we still have a bunch of terms to cancel out. Well, if you look at your terms and none of them cancel out, now you're going to do the reverse. You're going to use the parentheses and you're going to factorize something. So I'm going to group my terms, and this is how I'm going to group them. I'm going to say these two are inside parentheses. Now you can see that I have t in common in both terms inside the parentheses. So that means I can take t out. And now I have r and not r at the same time in the parentheses. Well, this is the expression that's always true. This is like saying you are passing my class or you're not passing my class. That's true for everyone. So this expression is 1. Okay, so now I have 2 times 1 plus not s, not r, plus not st. Is there anything else I can use here? And this is where you want to use your imagination, because the answer is, of course, yes. Let's take a look at these two terms. What if I group those two together? What would it get? Take a look. Once again, I can take t out, and then I will have 1 plus not s inside. But that is actually one of our theorems too. 1 plus not s always gives you 1, because this is an OR gate, and one of your inputs is always 1, so the output always has to be 1. So now we finally get to this expression. And at this point, it cannot be simplified any further. We've got not s, not r, or t. But that's, once again, it's a lot better than the expression we had on the very top. So this is finally our final answer. And you know you reach the end when you look at the expression and you can see that there are no more rules that could possibly be applied. So, are we done yet? Nope. We still have 4 more theorems to do. All right. So 4 theorems, that's rather much, right? But when you look at those theorems, they're actually one theorem written down 4 different ways. So this is how you look at this. You have one term right here. You have a lone guy. He stands all by himself. And there is another guy who is his exact opposite. In other words, it's that input inverted. And that other guy, the one that's exact opposite, is holding his girlfriend hostage, right? So I like to talk about Captain Obvious and, his nemesis, General Stupid, holding Captain Obvious's girlfriend, her name is Common Sense, hostage, right? Well, this is like a Hollywood movie, so the guy who's alone, he wins. So Captain Obvious wins, and in the end, you just have him and his girlfriend. So this is how it works. You find the term that stands by itself. Then you find its exact opposite. You kill the exact opposite, and that's what you have left over. So just like this guy stands by himself. This is his opposite, so I'm going to kill it. So in the end, I just end up with x plus y. Now, in my theorem number 17, my y that stands alone is no longer x. It's not x. Oh, that doesn't matter. He's still alone. His exact opposite is going to be x. So the opposite always comes. And in the end, I end up with not x plus y. Next one, I have x plus not x not y. So who cares if the girlfriend is not negative, right? It doesn't matter. It still works exactly the same. And the same deal happens over here. So this is very, very, very straightforward. And now finally, the one last thing we need to do today is to do an example of this. So I'm going to go ahead and solve this problem. So the very first thing you might want to look at is how many inputs you have and how many inputs in each term you have. So over here you have terms with 3 inputs. You have 2 of those terms. But one of the terms have 2 inputs. That's good, because that pretty much tells you that we're going to use one of those consensus theorems. So this is what I'm going to do. I'm going to group these 2. And you can see that they have p in common, both of those terms, so I can take it out. All right. So this one is the guy that stands alone, and this is his exact opposite. So it's going to die. And of course, it's best not to forget the. So now that we know that that loud S is gone, this is our expression. All right. Can I simplify something right now? Nope. So what do I do? Well, if you still have parentheses you can multiply out, you distribute. Okay, so let's do that. So now my expression looks like ES E not E. Yes. Can you put them together again? Sure. Now, once again, I can take E out. So which one is my long arm? Well, that's not cute, right here. So this one is the one that's out, and this guy right here is the 9. So my final result expression for that one is PS here, not here. That's S. Alright, can I simplify? Nope. But can I distribute? Sure I can. Distribute again. Can I simplify now? It looks like I have two of the same terms. Right here and right here. So PS plus PS is just PS. So my final expression is PS plus E not Q. And at this point, I don't think it can be simplified any further. Now, here's the deal, guys. The PowerPoint that I also put on the hub, it has a slightly different solution, and that's okay. There could be a different combination of rules that could give you exactly the same answer, and that's perfectly fine. It's not which rules you're using, it's that you're using them correctly and you're arriving at the right answer. Okay, so this is it for this rather long video, and hopefully this was helpful.